All right, this is the second recorded lecture of complex analysis, and today is 2026, February 23. And in the very first video, we look at three equivalent descriptions of holomorphic functions defined on a domain on a complex plane. So the next, like the ingredients that one must cover for complex analysis must be Cauchy integral theorem with the Cauchy integral formula. I bet for at least majority of the textbook or any references of complex analysis, the argument is of course so important. However, it's just a kind of like the straightforward that many just the textbook might just use the argument that so just apply Green's theorem, then one can establish the Cauchy-integral theorem with the Cauchy-Riemann equation, and then just look at the just the winding form, and by just using the winding form in a clever way, by just taking the puncture like the complement of puncture like this, then it established Cauchy-integral theorem, and it turns out that Cauchy-integral theorem and Cauchy-integral formulas are also equivalent for the definition of the equivalent definition of a function. This is sort of the story line that one should study when they first like learn complex analysis. But I kind of feel tedious, which is just a reviewing the very like the well-known like the result with the very known argument. I feel the following could be beneficial for many of the like the students who are learning complex analysis. So rather than just a standard like the fact, I'd like to look at the following theorem in this like the recorded lecture. So this is a second like the lecture of complex analysis that I put this as a last problem of the homework one of the my graduate complex analysis class that this is a has a name of the following like the name for this theorem, Cauchy-Green formula. And this could be useful even outside of the complex analysis context as well. So the statement is the following. So we have the omega inside of C, which is a bounded domain. Domain means connected open subset. And let us just assume for simplicity, the boundary is also smooth, meaning that if you parameterize this selective boundary, so the corresponding curve of the boundary is just a smooth function, meaning that infinitely differentiable. And let us just assume, suppose the function is just nothing but C1 up to the boundary, meaning that so interior, this like the partial derivatives are continuous, and we can just put the limit towards the boundary, then this like the limiting procedure, so the it is just continuous. That's the meaning of the C1 of the omega power. So make sure that this like the statement, I didn't require this function to be holomorphic. So which is the standard condition for the complex analysis to establish Cauchy integral formula, but I don't put that assumption with the intention in a sense that this is more general situation because holomorphic function must be C1, but converse is definitely not true. So then what we can claim, so for any point from omega, then we have the following integral representative. So f of z is same as the first expression is the familiar expression of the Cauchy integral formula. So integral over this boundary, then we have a following like the corner expression. So let me write as a f of omega over omega minus z d omega. So if this is the case, this is Cauchy integral theorem, but this is not exactly the case for the non-holomorphic functions. So there's an additional like the integral like the term, so over this omega. And it is written as the following. So the denominator is just the same, omega minus z, but the numerator is given as f of df over partial d omega bar. So that you can now see that where the holomorphicity should be used for the Cauchy integral, like the formula, like the formula or also theorem as well. So if this term is zero, so this recovers the original like the quotient theorem, like the formula. And this is the integration over like the omega. So to be reversed, let me write as a d omega bar wedge d omega. So this is the formula of the any C1 function, which is complex like the valued. So the curl is very like the clear. So one, if you just assume F to be holomorphic, then this achieves the quotient equal like the formula. That's very clear. So the proof is actually just the same as the standard argument of the quotient integral formula, but let me proceed this argument. And the slight like the different angle of this like the argument is that so the original argument of the quotient integral theorem and thereby quotient integral formula is to apply Green's theorem. So Green's theorem is quite intuitive in a sense that if it consider the either the car or the effect of the like the rotating like the amount, then if we just collect all those rotating amount, then because of the cancellation effect or like the inside of the like the collecting all those like the rotating effect correspond to the just the boundary integral of the given like the vector field. That's the meaning of the Green's theorem and the classical Stokes theorem. But it is very like the conceptual and miss like the intuitive for the complex analysis that so it is just a it seems just elementary so which looks easy but one need to notice that all those like the Green's theorem and or even for the holomorphic function integration those are coming from the integration of the vector field and the integration vector field and this even this like the expression it is the integration of the surface so that one need to consider so-called the integration of the differential forms. So the differential form, we need to look at integration of the differential one form that correspond to the integration of the vector field. We also need to look at the integration of the differential two forms and three forms and so on and so on. So the important like the perspective that one should equip it with complex analysis is that so we need to look at the integration with the differential forms, not just the just a scalar value like the functions and it looks elementary for sure, which must be elementary, I know it, but this like perspective is could be non-trivial for the at least for the beginners. So let me just put that perspective on this like the argument. That's the purpose of today's like the record so that the message I'd like to address from this like the record like the lecture is that it is very important to equip with the perspective with the integration with differential forms, not just a scalar value like the functions. So to establish this like the formula, so let's just fix arbitrary point first from omega. Then because this like the omega is a open set, so that we are able to find small positive epsilon sufficiently small to make the small ball center at this point must be contained in this omega. Then because we'd like to still apply the same argument, even though I will definitely skip to just provide the argument, the quotient theorem, quotient formula in the standard way. Those are well known. You can find any literatures, in my opinion, but this is still like the rewording. So, but the argument is actually, if you just compare for your own curiosity, it's just the same. So that we just look at the complement from this like the ball. And because we'd like to make this like the complement to be open as well, so also we like the delete all like the limit points from this like the small ball. And let's just call this by omega sub epsilon, which is clearly open because we take the complement of the like the closed set inside of the like that's the open like the set. So now we have a omega sub epsilon that makes the function that we want to consider, such as the effect of the denominator 1 over omega minus c, so that we don't need to worry on this like the omega sub epsilon because we already exclude the like the point z. So now I'd like to say we define one form we define one form. So let me just call this by alpha. So this alpha takes omega for the input, and this is one form. Let me start to put just a d omega. Omega is complex value, so d omega is just a dx plus I dy if you want. So, but I can also put the function, and let's just put the target function to establish. So f of omega over omega minus z. So this is the function that we'd like to consider. Then it is clear. Then f, this alpha is C1 on omega sub epsilon. So this is a one benefit of considering this omega sub epsilon. So then what we can say is we can apply this generalized Stokes theorem. So by Stokes theorem, so what we know is that the integral of this alpha along the boundary of this like the omega sub epsilon must be the same as the double integral over this omega sub epsilon of d alpha. So this is guaranteed. Then also we can see that this like the boundary of omega sub epsilon, if you draw the picture of omega. So even though I draw like something like the non-smooth, but this is assumed to be just smooth like the boundary, then we have this like the point Z somewhere inside of the omega, and we have also the boundary like this. So the reason way to think for tracking the boundary of this like the omega sub epsilon is that so in the counterclockwise direction, so we just follow this like the boundary first, like this, and then we go like this, so that we go like this, and then we go for the like the opposite like the direction, so that now we can easily see that from this like the description, so that so the boundary of the sky. So let's just put the like the different like the orientation. So because of this effect, so that we can say that this like the boundary of the omega sub epsilon consists of original like the boundary with the of course boundary of this like the ball, but let's just put the opposite direction. That's the meaning of this negative sign. Opposite direction. The reason is that we not just cancel this like the sign together. So we can say like this, so that the expression of this left-hand side with the alpha can be denoted as the following way. So this guy is same as first we have the same boundary with omega with the one from alpha. So this is good. And then because of the different like the orientation, so we start from the negative sign subtraction of the boundary of this small ball, the same alpha. Then this is now same as surface integral of this d alpha. So in order to establish, so now we are very close to the like the statement. So at least now we establish one term of the statement we'd like to get. So that it just is very clear that now we need to investigate this right hand side. So it is clear. Then now we need to compute d alpha. So again, this or argument I'd like to put as a message is that so we are dealing with the integration of the differential forms. This is the main message of today's like the like the lecture, like the record, like the video. So in order to understand, so let me just be clear that if we have a function, say g of omega, so we already fixed like the z. So we have this expression that we care. So for this function, so that this alpha, the one form we consider is same as a g times d omega. Then once you take the exterior derivative, the alpha, then the alpha you should get d of g d omega. Then you should use the Prog rule or the Leibniz rule, so that you should get first dg, and here's the important like, the point. You should consider the wedge product with d omega plus g d omega. Then by the property of the exterior derivative, if as long as you already have the d of something, d squared must be zero, so that you can ignore the second term. So that all you will get is just this guy for d alpha for d alpha. So still you need to compute this guy. So what is dg? So dg, so because now we have two input variables. One is omega for sure, but the another independent variable should be omega bar. So that you should see that this is same as partial dg over partial d omega plus partial dg over partial d omega bar d omega bar. This is the expression. And if you now apply this to d alpha, then you should get this guy. Then we also should use the property that if the for the wedge product, if you put same expressions, then must be zero. So all thing left is just a d omega bar wedge d omega with the corresponding coefficient function. So that you should get round dg over round omega bar d omega bar wedge d omega. This must be the expression of d alpha. So, and thereby, now we need to compute this expression as well. So now let's just relook at this expression. So this expression on where? So you can see that on like the omega sub epsilon, this guy is holomorphic. Of course, in omega, uh, I'm sorry. This is not holomorphic, right? So I should say in this expression, so what we can say that notice that because we didn't assume f is holomorphic, so that I can say this g is holomorphic. This is just I was just confused with the original argument of the Cauchy integral formula, but I cannot use it. So all we can say is 1 over omega minus z is holomorphic in omega. Of course, inside of the epsilon, like the omega sub epsilon for sure. So this is guaranteed because there's no omega bar by its definition of the holomorphic functions. So because of this, so when we take the partial derivatives on G, then now we have two expressions. One is the function f that we need to consider. Another one is this guy. Then we need to use the Leibniz rule. So the second, like the derivative must be zero. So this is one benefit that we are able to take. So and thereby, so that you can see that 1 over omega minus z, this is good. So we just get partial derivative on f with respect to omega bar. We get this. So therefore, the alpha is same as now the almost like the desired expression. Partial df over partial d bar over omega minus z times d omega bar wedge d omega. Now very good. So now let's just go back to the expression so that now we need to apply this to here. So let me just copy this entire expression. So this entire expression, oops, sorry. Let me just copy. So integration over boundary of omega of f of omega over omega minus c d omega is same as, so let me also just copy the same like the left hand side minus integral over the boundary of the small ball of the same expression. Now it is the same by using the just replacing the expression of d alpha. So this is now same as double integral over this omega sub epsilon, and the alpha can be written as what we obtain. What we obtain. So now all we need to just establish is just kill the effect of the as epsilon tends to just a zero. So now let me just skip that just pieces. There's a small exercise. So first you can check that this just follows almost immediate. So what you can see is that if you just take this guy So because those are just a standard, so that if you just take this guy as epsilon tends to zero, then you can establish by just looking at this expression that this is 2 pi I f of z. You should work just a bit because this is related to the effect of the winding form. But again, this is just a standard, so let me just skip to describe. And also, it can be also shown that so if you just take this integral as epsilon tends to zero, then because of the assumption f is as a C1 on omega bar, so that you can just kill this like the effect of the epsilon. And thereby this gives the like the result. So that now you can by just using by these exercises, so you can establish that 2 pi I f of z is same as the result that we needed to establish. My son is now outside from this room. He wants to play with me. So the first like the exercise is a little bit non-trivial, but still this is very like the well established. So I just want to leave that as a exercise. And if you have any like the issue, just leave some comment, and I will just try to put some like the note for so for some of the students who care the detail. So that's all I want to cover from let's say recorded like the video again. So this is a little bit like the slight generalization of the standard like the argument, the Cauchy integral formula, but I want to intentionally just investigate the statement without assuming the holomorphic like the function assumption. So from here, so that you can just get the Cauchy-Integral formula directly, and you can just compare with the standard argument from any of the textbook. So that's it for today, and thank you very much for watching this video. I will see you next time.